In this example, we want to apply the ideas of superposition to a simple beam, but it is somewhat unusual. It's certainly not a tabulated beam. So the beam is simple because it really has only one span. The unusual aspect of this beam is the support on the left. This support constrains rotations, but it allows free movement in the vertical direction. So in other words, at this support, theta is equal to 0, but v is not specified. On the right, we have the standard roller, which constrains the deflection. The beam has length L, constant bending stiffness EI, and loaded by a force P in the middle. Let us begin with the free body diagram. So the reaction forces are shown here, the vertical force and the couple. There is no vertical force here, and as usual, I don't show the horizontal force. And if I take this free body diagram and write down equilibrium equations, I will obtain this free body diagram showing the actual forces. Of course, R must be equal to P, that's sum of the forces, and the couple produced by these two forces is counterclockwise. Its magnitude is P times L over 2. Therefore, this couple must be a clockwise couple, PL over 2. So, this free body diagram can be related to this cantilever beam. Indeed, if I draw a free body diagram for this beam, I will recognize that the reaction forces here are exactly the couple PL over 2, and the shear force is equal to 0. And of course, this beam is tabulated. What is wrong with this beam, at least as compared to the original beam? In the original beam, the deflection here is 0, and the deflection here is not 0. In this beam, it is 0 here and something at the tip. So to deal with this, let me think of V1 of L as the displacement at the tip of this beam. And now what do I need to do? I need to make sure that I add something else, and this something else will make this deflection equal to 0. So I say the original beam will be equal to this beam plus this loading. So what does this loading do? If the displacement at the tip is V1 of L, then I will superimpose it with a negative rigid body motion upward. If I put these two guys together, right, I will immediately conclude that by construction, the displacement of the tip is 0. The deflection here is whatever is dictated by rigid body motion, because there is no displacement coming from this case, right? And basically, all I have to do right now is to solve for this, then add rigid body motion of the second beam, and I'll be done. So let's see how it's implemented. So here's my first loading. Of course, it involves two forces, so I'll have two tables. That's the displacement of the tip due to the point force at the tip, force in the middle, So now let's see how it proceeds. Minus PL cubed over 3EI comes from here. The reason I have minus is because my force is up, here the force is down. Now the second table is evaluated for A equal to L over 2. So I plug in L over 2 here and L over 2 here, and as a result I obtain the displacement minus 11 over 48 PL cubed over EI. Minus indicates that the tip moves up, and it's not really that surprising. This force is more potent than this one. And now my second loading says that V2 of x, right? So it's rigid body translation. So for all points is constant, and it's equal to minus V1 of L, which means that every point moves down, all right, by 11 over 48 PL cubed EI. This includes this point, right? So 11 over 48 EI is the displacement at L at x equal to 0. Now, let's put the superposition in place. V at L over 2 is given here, right, from this table. Now, for this case, we evaluate at x equal to A. So A is L over 2, but that's the contribution of this force to the displacement in the middle. And finally, we have the contribution from the rigid body motion. And now we will add these three guys together, and we will obtain the answer that involves minus 5 over 48 plus 1 over 24 plus 11/48. It is 1 over 6 PL cubed over EI.